maybe? I don't know. I have to look at that more.
Okay, I mean, yeah.
And there's like a huge amount of applications I found. Yeah. Mainly in like signal processing and physics.
Right. Yeah, that's great. I think Ryan was specifically avoiding signal processing. So, anything you have to say about signal processing?
My friend's taking a class in like electronic signals. He's an EE major.
Okay.
And they cover Fourier series in like that context. Like
Okay. Yeah, that makes sense.
signals.
Mm-hmm.
Your project's on not yeah,
conformal mapping.
conformal mapping. I do not know what that is.
It's basically you go from one region to another by using a one-to-one analytic function.
Oh, so okay.
There are some other constraints that you have.
Yeah, is it like a injective or a bijective
Yeah.
function and it has to have an inverse or something? So it's like a holomorphism?
I'm not sure.
It's stronger than that.
It's stronger than holomorphism?
Yeah, yeah. Right, there's holomorphicity,
It's what, between two analytic functions?
well, it's,
Bijective?
well, really, you have to start talking about complex manifolds to talk about things that are holomorphic,
Yeah.
right? They're things that preserve the holomorphic structure, i.e. some topological structure described by holomorphic or analytic functions, right?
Yeah.
Conformality is a stronger condition, right? It has extra properties like such as preserving angles,
Right.
right? So yeah, it's more than that.
So when we were talking about like taking a simply connected region and deforming it into a point, and then back into any other simply connected region, that is not a conformal mapping, right?
Yeah, right. That's actually, remember, we call that a continuous deformation. That's not even analytic.
Okay, I was confused because they were going through such painstaking.
Great lengths to do something similar to that without just being like, we can just shrink to, yeah.
Right, yeah, they're doing it for a unit disk instead of a point.
Uh-huh, uh-huh.
And the proof is so long and complicated.
Right.
How do you go about like defining a complex manifold?
Well, how do you define a,
real manifold?
there's a, word manifold is actually pretty ambiguous, right?
Yeah.
Because you have to determine what it means for your coordinate functions. Like what, like there are notions of like piecewise continuous manifolds, which are not very nice, right? Because they can like have all kinds of weird sharp edges.
You consider one of the differential geometry that I forget the name, but it's like some famous one that if you get the origin, the second partials are not equal. The second best partials are not equal.
So in other words, you're not continuously differentiable.
Yeah. Some weird.
Yeah, there's a lot to say about that. I don't think I can give you a sufficient answer in the time before we're supposed to start, which is actually right now. Okay, so we're in the midst of some example, right? Where I gave you some function which has two poles, right? At d equals 1 and d equals 2. I'm actually asking you guys to,
Yeah.
I don't exactly remember where we left off.
We just finished part A, so we just found the Laurent series for that the functional function inside the unit disk.
Okay, great. So we completed part A.
Yeah. Yes.
Okay, good. So let's just remind ourselves what parts B and C are, and then write them out. Yeah. Okay. So we have left to do to find Laurent expansions of the function 1 over z minus 1 and z minus 2. In each of, and I'll just start with B since we had A last time. Right? Is annulus, sorry, not equal, between 1 and 2, and the complement of the closed disk of radius 2. Okay, so again, reminder, using partial fractions, we transform this function into the following. B minus 2 minus 1 over z minus 1. Okay, z, sorry, not 2 minus 1. Okay, so here's the thing. In our region for part B, notice that our Laurent expansion for 1 over z minus 2 is just the same, right? Because, I'm sorry, our Laurent expansion from part A for the term 1 over z minus 2 is the same in this region B, right? Because we're still inside the disk of radius 2, which is what we used to manipulate this into a geometric series that converges, right? Which is our general strategy for generating Laurent series, right? Or that's what we've seen so far. Yeah. Okay, so let's record that. Note 1 over z minus 2 has same Laurent expansion in B as in A. However, necessarily it must be different for the negative 1 over z minus 1 term, because the singularity for this summand lies in between the region A and the region B. Right? So we have to generate a new Laurent series for 1 over z minus 1. So we find a new Laurent series for 1 over z minus 1. Okay. So let's proceed as we had been in our last example, right? How do we manipulate this to look like a geometric series which converges?
Factor out negative sign.
Well, okay. So if we factor out the negative sign, what do we get? We get 1 over
Minus z.
1 minus z, the modulus of z. Right? Now look at the conditions on the modulus of z. We're strictly greater than 1.
Oh, yeah, so it doesn't.
So we have to do something different here. Right? This is, if we were able to just factor out the, say again,
Factor out z.
factor out a z.
1 over z. 1 over z.
A 1 over, yeah, a z from the denominator.
Yeah.
Right? Yeah, good. Z. Okay, good. So now, in this region, right, where we have the modulus of z between 1 and 2, this is something that a geometric series converges to, right? So we get still the factor of 1 over z out front, times the sum j equals 0 to infinity of 1 over z to the j, or if you like, 1 over e to the j plus 1. So all together, we'll just combine our previous Laurent series from part A for 1 over z minus 2 and subtract the Laurent series that we just generated. So what do we get? Remember from Tuesday, the Laurent series for the term 1 over z minus 2 is negative z to the j divided by 2 to the j plus 1. And we subtract what we just computed. Over e to the j plus 1. And, you know, I would say don't work too hard to try to combine your series into a single expression for some end. This is a perfectly acceptable way to leave your answer. But for clarity, sometimes you might want to know some of the terms. So what do we get here? We get, oh, really, I have infinitely many negative terms here, right? So let's just say, for illustration purposes, I get 1 over z squared minus 1 over z minus 1/2 minus z over 4. I extend infinitely in both directions. Okay. So this is we'll see the importance of this and further ways to characterize this later today when we have infinitely many negative terms that imply something about the function that we're considering. Okay. Specifically, it implies the type of singularity that we're dealing with. That's what we'll do after we do finish this example. We'll talk about the classification of different types of singularities, specifically isolated singularities. Right? Okay. So there you have it. Now for part C, what can I say about my series developments for these separate summands?
Well, the series development for 1 over z minus 1 is the same as B.
Yeah, right. We can reuse what we just computed for 1 over z minus 1 because the singularity of this is in the same part of the plane as relative to this region and this region, right? They both have z equals 1 on the inside, right? Okay, so reuse this from B, but now of course we've gone from being the modulus of z being less than 2 to the modulus of z being greater than 2. So the relative position of the singularity of 1 over z minus 2 has changed from part B to part C. So we have to redevelop the Laurent series for 1 over z minus 2. Okay? And calculate 1 over z minus 2 again. So, how will we transform this into something a geometric series converges to?
Factor in z again?
Yeah, we'll just factor out a z, a 1 over z. same as before, right? So if we factor out a 1 over z, we get 1 minus 2 over z. Okay, same old trick. The sum from j equals 0 to infinity of 2 divided by z to the j. We get 2 to the j over z to the j plus 1. Okay, so this actually combines a little more nicely, right? Because we have the same denominator by chance. So it's not so hard to just push them together. So I'll do just that. Want to have an eraser again? Oh, good. Okay. What do we get here all together? Sum from j equals 0 to infinity of 2 to the j minus 1 divided by d to the j plus 1. Or, if you like, we get again something with infinitely many negative terms. Uh, 7 over 4. Okay, so the important thing to note here is that the Laurent series development depends on the region. Depends greatly, entirely on the region that you decide to come up with this series expansion. And similar situation for Taylor series, right? That is to say, Taylor series might be different at around different points. Same here for different annuli, where we allow the punctured disk to be considered as an annulus, right? With inner radius 0. Okay? So, I just want to, well, let's postpone this last example because we're going to use it in a very important conclusion that we're going to make at the end of the day. So we'll say it closer to the time that we make that conclusion. Okay, I know we've had scant practice at finding Laurent series, but I think you get the idea, right? So now I want to talk about classifying the zeros and singularities of an analytic function, or a function which is analytic at all but finitely many isolated points, right? That is, we have finitely many isolated singularities. And what I hope we can get to by the end of the last class on next Tuesday is a method of computing integrals that relies on being able to calculate Laurent series quickly. Okay? It's actually faster than the Cauchy integral formula in many cases, okay? Which is already pretty fast, but I hope to get there by the end of Tuesday. Okay, so anyway, let's discuss a little more systematically zeros and singularities. We've touched on these topics before, but really we only talked about polynomials and rational functions. Now, we're going to expand our discussion to analytic functions in general. Okay, so so here's a combination theorem definition. Okay, so let's let F be analytic. At Z naught, then F has a zero of order M if and only if f of z is equal to z minus z naught to the m times g of z where g of z is analytic at z0 and g evaluated at z naught is not equal to 0, and just as a matter of terminology, a 0 of order 1 is called simple. Okay. So, tell me how to prove this. I'm not actually going to commit the proof, but how do I proceed in demonstrating this fact? What do I know about f? What information do I get by saying that f is analytic at this point, z naught?
It has derivative.
It has derivatives, which means we can
Use
Look-
associated row formula?
we can look at its Taylor series, right? Because it has all derivatives. Its Taylor series is well defined, right? So in sketch, proof. Look at the Taylor series of f at z naught. And note that it's first m minus 1 derivatives the nth coefficient in the Taylor series not equal to 0, right? So then just let g of z, not to am minus z naught the m am1 z minus z naught to the m plus 1. We have some function g, which has this Taylor series, right? Remember, a result when you start discussing series and their convergence is that if the series converges, you can cut off finitely many terms from the beginning, and it will still converge, right? So whatever this series happens to converge to is the function g that you get as the part which is not 0 at z naught. Okay. So that's pretty sketchy, I believe so, but I think the idea is clear. Okay, so we're going to do a lot of stuff like this where we look at a Taylor, or more often a Laurent expansion, and see what we can say about expanding it or decomposing it in this fashion. Okay? So, here's a corollary. Right. If f analytic such that f of z naught is equal to 0, then f is either identically 0 I should say locally in a neighborhood of z, of z naught, or there is a punctured disk about z naught, where f has no zeros. You kind of did a problem very similar to this on the last homework, right? Where we were actually just analyzing the sign of the sum of the moduli of our, or actually the size of the sum of the moduli of our coefficients, right? So this is a similar type of result. Let's see how we prove this. Okay, so what do we know? The Taylor series must converge in some circular neighborhood of z naught, right? if all coefficients are 0 in the Taylor series, and identically 0. Okay, that's the first case. Otherwise, what happens? Otherwise, let's just let m greater than or equal to 1 be the smallest index with am not equal to 0, the coefficient in the Taylor expansion. Then, by the construction I outlined, we know that f must have a 0 of order m at z naught, right? Because that's exactly what I said g is, right? The truncation of the Taylor series of f, cutting off the first m minus 1 terms, throwing them away. Of course here, they're 0 in our construction, right? Okay, then f must have a 0 of order m at z naught, which from the theorem tells us that f of z equals z minus z naught to the m times g of z with g of z analytic at z naught and g of z naught not equal to 0, right? Just what our theorem said. Okay, and therefore, there exists a disk about z naught, where g of z is non-zero. Why is that? Remember, where g of z is analytic at z naught, which means it's actually in an open neighborhood around z naught. It is analytic. And analyticity implies continuity. This actually depends only on continuity, right? That if you're non-zero at a point and you're continuous, then you have to be non-zero at some neighborhood around that point. You can't just jump down to 0. Okay? So I'll put that in parentheses. Okay. Which we'll give a specific name. This disk of radius delta. Okay. So what does this imply? Well, the Taylor expansion for f and g agree, right? That's how we came up with the Taylor expansion for g. Just the Taylor expansion of f. Right? So this is to say in, sorry, 0 strictly less than z minus, the modulus of z minus z naught, strictly less than delta. Okay. So, continuity in disguise, really, or rather, using a much weaker consequence of our sledgehammer of analyticity that so tightly confines what a function can do. Right? Okay. So, I just wanted to make a quick comment about something that you said sometime last week, I think. So the way that we phrased our definitions, I just want to point out that the order of a 0 has to be a whole number, a positive integer. Right? And this is because, well, think of example for like z to the 1/2 power. You might want to say, oh, well, it's just the power, it has a 0 at z equals 0, right? You might want to say that it has 0 of order 1/2. But the problem with that is, remember, we required this in this discussion, that our functions be analytic around the given points that are zeros, right? And remember, we have to choose a branch for the square root of z, right? So that's just an example to try to illustrate why, in fact, the order of a 0 has to be a whole number. Because otherwise, you lose the analyticity condition on your function that has a 0 at that point. Okay. All right. Good. So now we're going to get to the main classification of singularities. There's 3 types of them, if they're isolated. Okay, so let's suppose f has an isolated singularity. Isolated. At z naught. And let the Laurent expansion of f in the following annulus, or really I should say punctured disk, be given as follows. Use our compact notation. Then we have the following. 3 cases. 1. If a sub j equals 0 for all j strictly less than 0, we say f at z naught. Okay, furthermore, if a sub negative m is not equal to 0 for some positive m, but a sub j is equal to 0 for all j strictly less than negative m. Then we say z naught is a pole of order m.
That's A sub negative M.
A sub negative m, yeah. Sorry if that was unclear. Right, why do I bother to say negative m and that m is positive? Because we want to incorporate that into the classification of what z naught is, right? It's the order of the pole. Okay. I guess I should say for f. Okay. You can probably guess what the third case is, right? What do you think?
A non-removable singularity.
Yeah, how is that described?
Well, I hadn't gotten to that part yet.
Okay. So yeah.
A sub j is never is.
Yeah, never.
Yeah, exactly. All of the negative, or there, sorry, not all. There are infinitely many non-zero negative coefficients. Okay, so good. If a sub j is not equal to 0 for infinitely many negative values of j, we say z naught is an essential singularity for f. Okay, so cases 1 and 2 should seem kind of familiar to us, right? These are just like the singularities of rational functions, right? If we have a ratio of two polynomials and we have a cancellation of factors, we call that a removable singularity, right? Likewise, if we have powers of some linear polynomial in the denominator, we call that a pole of order m, depending on the power. We're doing the same kind of analysis, but now we're using the Laurent series that represents an analytic function, right? Because in general, we can't just say, oh, we'll divide by or multiply by this linear polynomial raised to some power and get a sensible thing, right? So we have to use the Laurent series to do this algebraic manipulation, and it works out quite nicely in these two cases, 1 and 2. Case 3 is altogether different though, right? Because this doesn't occur for a rational function. polynomials are products of finitely many linear polynomials, right? So our goal now is to classify the behavior of f near each of these types of singularities, so that we can come up with some qualitative description of how a function behaves around each of these types of singularities. That is to say, when I say qualitative, I mean we'll come up with conditions to recognize these types of singularities that don't require us to necessarily compute the Laurent expansion. Okay? We can deduce the type of singularity simply by looking at the behavior of the function around near the singularity. Okay. So first, we'll go in order, right? We'll start with removal of singularities. I'll give you this silly kind of example. So let me ask you to find the Laurent expansion of the following function, f of z is defined by sine of z if z is not equal to 0, and 5 if z is equal to 0. Okay. So first, let's note that, oh, sorry, I didn't give you all the information that you need here. Where do I want you to compute this Laurent expansion? In the region the modulus of z strictly greater than 0, punctured plane. Okay, so first of all, let's notice that this is possible, right? Because this function is analytic in the region that I asked you to compute the Laurent series in, right? Because if we're excluding the point 0, this is just sine everywhere. We've constructed this pathological thing to be discontinuous, so certainly not analytic in the entire plane. But it is analytic in the region that I ask you to find the Laurent expansion. Okay? Okay. So note f analytic in this region, so must have a Laurent expansion. Furthermore, we didn't actually talk about this except briefly at the beginning of the term, right, where I told you you could deduce the formulae for sine and cosine, the complex value functions, from the Taylor series of the complex exponential function. These just match, right? You just replace x's with z's. Right? So hopefully we remember the Taylor series for sine of z, or rather, you remember x, now just insert z's for the complex case. Right? And if you want to quickly justify this to yourself, remember we showed that the derivatives are the same for the real valued sine function and the complex valued sine function. Right? You formally take the derivative in the same fashion, right? Derivative of sine is cosine, derivative of cosine is negative sine. You get the same cyclic sequence of derivatives. Okay? And if you evaluate them at a point, well, you're just getting some complex number out, but it'll fit the same pattern, right? So we must have a Laurent expansion, and we we know the function g of z, which is just defined to be sine of z everywhere, has the following Laurent expansion. I'll write it out in term form. Right, this is hopefully familiar, right? It's just the odd powers of z with alternating sign. And of course the factorial denominators. So what is this telling me? It tells me that the Laurent expansion of f has to be the same as the Laurent expansion of g. Right? So f and g have same Laurent expansion in this region. Sorry, 0. Okay. So this indicates a general phenomenon. Okay? So z equals 0 is a singularity of f, right? And what we've done is found a function which is analytic at the singularity of f and agrees with f everywhere that isn't singular. We've removed the singularity by constructing g. Okay. So we've removed the singularity of f at g equals 0 by construction of g. So this isn't a proof, but the takeaway from this is that we were able to find a Laurent series for f that has no negative terms. Right? That's the defining characteristic for what it means to be removable. Right? That is equals 0 is a removable singularity of f, since Laurent of g has no negative terms. Okay. So, right. This is what the heart of the intuition of being a removable singularity is all about. A removable singularity is just some problem with the definition of the function, right? It's because we did this silly thing of saying that sine has the value, or I'm sorry, f has the value 5 at 0 and sine of z elsewhere. So this characterizes removable singularities in general, right? It's just a problem of like, oh, we can say that our function, we can construct a new function by just saying our old function has the correct value where it was undefined or discontinuous before. Okay? So let's look at another example. Let's consider the function f of z is equal to sine of z divided by z. Okay, so we have a singularity at z equals 0 here, right? And if we want to classify what kind of singularity it is, we should come up with the Laurent expansion of this function and analyze the terms. In order to do that, since my bottom is just a polynomial, I'll just factor that out and write my Laurent expansion of sine of z. And then I'll get some cancellations, right? Because the denominator is in a particularly nice form. Right? Okay, so what do we get again? It's z minus z cubed divided by 3 factorial plus z to the 5th divided by 5 factorial minus, okay, distribute the 1 over z, what do we get? 1 minus z squared divided by 3 factorial plus z to the 4th minus 5 factorial. Okay, so just from the definition, right away, we see that we still have no negative terms in our Laurent expansion, right? So z equals 0 is removable. For f of z. Now, based on my ramblings for the past several minutes, I should be able to construct a function which agrees with f everywhere that's analytic at z equals 0. How do I determine that value?
We already have the whole.
Yeah, I just plug in 0 to the Laurent expansion, right? And see what I get. 1. Okay? So, g of z equal to sine of z divided by z for z not equal to 0, and 1 for z equal to 0. I should say is entire, right? It's analytic in the entire plane. So in general, you know, it's most often not the case that you can just redefine a function in this way and get something that's analytic at your original singularity. But for the special case of being removable, this is always possible, right? And exactly what we did is how you get this alternate value. After you simplify your Laurent expansion and get show that it has no negative terms, then you're able to just plug in the singularity. And all the terms with a positive power will go to 0. Okay? Good. Let's take a 5-minute break. And then we'll talk about poles. Oh, actually, we'll talk more about removable singularities for a little bit. I'm really excited to get to essential singularities. This is going to be good.
Did we ever do this in any other class? Because For some reason, this whole process, I feel like I'm deja vu. I can't remember why. No,
I
right?
don't think so, no,
No, yeah, I had no
I can't
idea.
remember doing this previously.
Yeah, okay, never mind.
But, if it's familiar, that's,
It's just making too much sense. It's not why.
you use that to your advantage.
Did you say anything about the paper before I got here?
No, no. Yeah, I had asked, everybody to turn in some form of a draft or another by today. I just meant like by midnight. I mean, I'm not grading you on turning in a draft or not. I just wanted to see how your progress is coming.
Can we go over 5 pages?
Yeah, sure. You can make it as long as you want, that's fine.
Does the draft have to like reflect how long the actual paper will be?
Wild.
No.
Should we just like send progress?
Mine's so
Yeah, just for any form of progress is
easy.
fine. You don't stress about making it look good or formal
What did you say you were doing?
in any way. I just wanna like know how you guys are doing.
And just email it?
Yeah, I didn't make an assignment on Canvas or anything, so just emails are fine.
Oh, like a wire straws?
Yes, I don't know how to pronounce it.
Fire straws.
Wire straws?
Fire.
Fire?
It's because
Oh.
it's German.
It's German.
Oh, that's cool, of course. Fire straws. It's actually pretty cool. I'm gonna bring soap to class too.
That's like
Can I
a-
bring soap in? Can I do like a whole
Yeah.
demonstration?
No, that's definitely COVID safe, right?
Yeah, I think so.
Someone with like bubbles or whatever?
Yeah, so basically like soap film takes the like, I guess like smallest area possible within something. So for example, if you have like a cube, I don't want to give away my whole thing, but whatever. Okay, let's say you got these two trees over here. Make the least or shortest path distance to connect them all. It's not gonna be any connection here. It's gonna be kind of like a force that comes here in the middle, it's connected. But once you make that into a three-dimensional space and you get a cube, and you dip like a wire frame, the soap won't cover the cube completely. It'll kind of, with the surface tension, pull it inside to the middle. It's actually sick. I don't know, I'll show you guys later.
Like liquid soap? Like liquid soap?
Yeah, literally liquid soap. Like,
Is it like geodesics and stuff? Like shortest paths between things?
I don't think so. I'm not that smart. I can't tell. Couldn't tell you. Oh, here, I'll show you. One thing, soap film. Where'd this go?
I feel bad, I'm not gonna have like a live demonstration.
Yeah.
Uh,
Kinda hard to demonstrate quaternions in real life.
It's like maybe eight different areas.
Like this. So like this. Soap, for some reason, takes the least amount of area possible. Minimal surfaces. Pretty nice.
Is that the principle of leaf basketball? That's physics.
Oh,
right?
wait, those fit in picture.
Soap. It's crazy, guys.
Okay, I guess we should continue for now, but this is good. I'm glad to see some enthusiasm for our upcoming finals. Right, I make kind of a big deal about constructing this function g, which is analytic, where f had a removable singularity. And that's because this gives us a characterization of how the function f behaves near the removable singularity, right? So remember, this is a general phenomenon, right? I just showed you an example, but you can always do this for a removable singularity. You can construct some function which agrees with the function with the removable singularity, which is analytic at the removable singularity. Since g of z analytic, at z naught, its modulus is bounded in some disk centered at z naught, right? So, what does this tell us? Remember, f and g share Laurent expansions. So what this tells us is that the original function f is bounded in some punctured disk centered at its singularity. Okay? So that is to say, we can't grow infinitely large near a removable singularity. Okay? This implies that f is bounded in modulus in some punctured disk. Centered at z naught. Okay, so what do we have? I've just justified the following lemma. It's kind of what I said is a proof, but I'm not going to say anything more formal than that. I'll just give you the conclusion here. With f as a removable singularity, at z naught, then we have the following qualitative descriptions. Right? What I just said, f of z bounded in some punctured disk has a finite limit. As z goes to z naught. And how do we calculate that limit? Well, the Laurent expansion allowed us to just plug something in to. This is actually the limit, right?
Yeah.
Okay, good.
Use L'Hopital's rule. On the thing, on the F of Z.
Well, in this case.
Yeah, back in Calc 1.
In this case.
Yeah.
That doesn't apply in general,
Yeah,
right?
yeah.
Because you might not be 0 over 0 at a removable singularity. Okay. And thirdly, what can we say about removable singularities? Right, what I've been saying all along, f of z can be redefined at z naught. So the new function is analytic at z naught.
This is kind of like what we do when we have like some rational function and we factor out the factor that appears on the bottom and cancels them, right?
Yeah, it's just like that. But now we don't have to restrict ourselves to being a rational function. Yeah. Good. Okay. So if you've looked at the homework, the final homework, I ask you to prove the converse of this, right? That is to say, if f has a singularity at z naught and is bounded in some punctured disk around z naught, then it must be removable. And that's on the last homework. Good. So I'll just remark. You'll prove the converse.
Do you have any hints?
Think about it. That's my hint.
So no.
Right. Okay. So now let's address the case of a function which has a polar order m. Okay. F of z with pole of order m at z naught has Laurent expansion This is again just going back to the definition, a sub negative m divided by z minus z naught to the m plus a sub negative m plus 1, I'm sorry, no, m minus 1 divided by z minus z naught to the m minus 1. I know this gets really confusing with the negatives in the subscripts, so just bear with me. If something's unclear, just ask.
So you're adding 1 to the subscript of the A and subtracting 1 from the power of the denominator.
So I'm adding 1 to the index, remember, because
Right,
this is,
okay,
yeah,
Okay, that makes sense.
because yeah, we're a negative index. Add 1 so we subtract.
So like that, like if a sub negative m, if that was like the second index, your next index would be -3 and not -1.
Wait, sorry, say that again.
So like if that was your index, like the first term was like indexed at 2, the next one would be
Negative 1,
-1. Okay,
right? So
it's
2 minus
getting
1.
closer to 0.
2 minus 1, negative, yeah.
Okay.
up to a negative 1, and we have the power negative 1 on z minus z naught, plus a naught, plus a 1 z minus z naught, and then I go on indefinitely to the right. You can have as many positive power terms as I want. We're talking about poles or singularities. Okay, right. Oh, it's important to say with a to the negative m, I'm sorry, a sub negative m, not equal to 0. Right, because if it was equal to 0, then I would actually have a pole of order m minus 1.
M minus one or M plus one?
Minus 1.
That makes sense, okay.
Yeah, I guess pay attention to the power on the binomial.
And there's nothing stopping all the terms after a sub negative m being 0, right?
Yeah, that's right. You could have zeros here.
Those could be all 0.
Yeah, that is allowed. Yes. Okay, but the important point is this is from the definition, but we're going to use this explicit fact in our investigations. Okay. So right. Of course, whenever I talk about a Laurent expansion, I have to talk about the region in which it applies. So we say valid in some punctured disk centered at z naught. Okay. So just like last time, I'm just going to proceed by way of example, and then we'll try to generalize from that. Okay. Not my usual style, but again, we're a little tight on time. Okay, so e.g., let's consider the function f of z equal to sine of z divided by z to the 5th. Okay? Describe the singularity to me. How would we classify the singularity at z equals 0?
A pole of order 5.
A pole of order 5. Okay, what do we think? Do we have anybody agree with that?
Not gonna be order 5.
It's not going to be order 5. Okay. So one
Order
dissent.
4.
Yeah, I think
Yeah, order 4.
Order 4.
Yeah.
Okay. So what's going on there? Why is that?
The Taylor series of sine of x has the first term is x, so you'll cancel, or sorry, z. So you'll cancel 1.
Yeah, exactly. Right. So remember, now that we're not dealing with rational functions, we have to look at the Laurent expansion naively to determine what type of singularity we have. And when we do that, well, let's see what happens when we do that. Right? So this is a fairly simple example that we've already been working with most of the components of today already. So we'll just take the 1 over z to the 5th out front and look at the Taylor expansion of sine of z, right? Which is z minus z cubed divided by 3 factorial plus z to the 5th divided by 5 factorial. Okay, so now let us divide by z to the 5th each of these terms. And what do we get? 1 over z to the 4th. Cancellation, just like Luke and Joe deduced together over there. Minus 1 over 3 factorial z squared, right? Plus 1 over 5 factorial, so on and so forth, right? And this also illustrates your question, right? You can have terms afterwards that are 0. It's just the smallest one which is not 0. the largest negative one, if you like. Okay, so, good. Now we see explicitly that this is, in fact, a pole of order 4.
Did you say if, like a pole of order 0 would just be a removable discontinuity?
Yeah, you could, I think even if you look at some older textbooks, you might see that. I think it's typical these days to treat that as a separate case. For, not very important reasons, but yeah. I don't think anybody would be confused at what you meant if you said a pole of order 0. But I don't know why. I actually don't have a good answer why people decide to make that distinction. Okay. So, right. We have a pole of order 4 at equals 0. Okay, just a piece of terminology. A pole of order 1 at V0 is called, you can probably guess, a simple pole. Just like we had a simple 0, right? Okay. So, here's a series of lemmas. If F has a pole of order M at Z0, then the modulus of Z minus Z0 to the L times F of Z goes to infinity as Z goes to Z0, or L strictly less than M. While if we multiply Z minus Z0 to the M by F of Z, you get a new function which has a removable singularity. At Z0. Okay, so in particular, the modulus of F of Z goes to infinity as Z approaches Z0. Well, there's kind of an answer to your question right there. If I allowed poles of order M to be where M is 0, I couldn't make this statement, right? The pole of order 0 is just a removable singularity, and the modulus does not go to infinity as Z goes to Z0, if Z0 is removable. So it's still a terminological difference, but then you would have to say this holds for poles of order M greater than 0, right? So I guess it's easier to just treat it as a separate thing because the behavior is quite different. Maybe that's the reason why. So, oh man. Okay, let's just prove this. Right, so in some punctured neighborhood, some punctured disk about Z naught, we have the following, Z minus Z naught to the M times f of Z is equal to the following, right? We just get a sub negative m plus a sub negative m minus 1 times z minus z naught. Right? I get a lot of cancellations when I multiply it by z minus z naught to the m. Right? Okay. So what can I deduce from this? Since there are no negative powers of z minus z naught, z minus z naught to the m times f of z has a removable singularity. At z naught, right? That was just our definition of removable singularity. That is, the Laurent expansion has no negative terms. Sorry, I really should say negative powers of z minus z naught. Right? Who knows the sign of a sub negative m? Okay. Also, since a sub negative m is not equal to 0, right? Remember, because we have a pole of order m. We have the following. The modulus of z minus z naught raised to the L power times f of z is equal to the modulus of 1 over z minus z naught raised to the m minus L power times z minus z naught raised to the m power f of z, right? I just did a little algebra here. Okay, which in turn is equal to a sub negative m times the modulus of 1 over z minus z naught to the m minus L, which goes to infinity as z goes to z naught, right? So what do I do here? I just split my modulus up according to this factor. The modulus of this, oh, I'm sorry. Oh yeah, right. This is I wrote a technically wrong thing here, right? But as z goes to z naught, I get for this term this term, I get a sub negative m. And this term goes to infinity. So the whole thing goes to infinity, right? I shouldn't have written an equal sign here. But I think you know what I mean, right? After I make that explanation. Sorry for that. Okay. Good. So, right. Okay. Here's what I'm going to do. There's a couple more important things to say about poles of order m, and I'll say them on Tuesday, the beginning of class. But I want to finish today just talking about what happens with an essential singularity, just to give us a complete picture of what an isolated singularity can be. Okay, so before I do that, just think about what we've said so far. The qualitative behavior of a function which has a removable singularity at z naught is that the function is bounded in a neighborhood of z naught, right? So what we'll do on Monday is finish the story for poles of order m, but what happens is that a function with a pole of order m at z naught goes to infinity in a neighborhood of that pole. And when I say goes to infinity, I mean that the modulus is arbitrarily large. I don't mean that it goes to infinity in the extended complex plane. Okay? So it seems like, well, seems like as bad as it can get, right? It's like, what is there besides being bounded and having a finite limit and going to infinity in modulus? Well, let me tell you, this is actually quite hard to prove. We don't have the tools to do it, but I asked you to prove a weaker result along the same lines in the problem set that's due next Wednesday. And this is due to Charles Picard, was actually a professor of engineering. France. He's been a really brilliant guy. A function with an essential singularity assumes every complex number as a value in an arbitrary neighborhood of the singularity. With possibly one exception. Okay, so this is way worse than just going to infinity in modulus. Every single complex number can be found in an arbitrarily small neighborhood around the singularity as a value of your function. Yeah, this is Very bad behavior. Okay? And then, this is even more bizarre. There might be exactly one value that it doesn't assume.
But does it vary for different functions?
Yeah. Yeah.
I thought you were saying equal 0 and 1, but it changes?
Yeah. Yeah. So, okay, like I said, we're not gonna be able to prove this. It takes a lot of work. But what we can do is verify that, this happens for a function that we know has an essential singularity. Okay? So, consider, f of z equal to e to the 1 over z. Fairly innocuous, easy to write down, right? Clearly has a singularity at z equals 0. Furthermore, if you believe what I said before, the Taylor expansion for e to the x is the same as e to the z, right? Because the derivatives are all the same formally, right? Okay, so what we can say is that what is our Laurent expansion? Sorry, I wrote this down in a different part of my notes. Right.
It's 1 over z to the n divided by n factorial.
Yeah, right, exactly. It's 1 plus 1 over z plus 1 over 2 factorial z squared plus 1 over 3 factorial z cubed. And this is the same as the Taylor expansion for e to the z, but now I've just replaced z with 1 over z. Okay? So this tells us from the definition that z equals 0 is essential. Right? Infinitely many terms with negative exponent. Okay? Right. So, what do we do? What do we do? So, first, note e to the 1 over z is never 0. This is from the basic properties of the function. Right? Okay. So that's, for this function, that's the one exception. Okay? So let's then take c not equal to 0, a complex number. Okay, then let me remind you of the multi-valued function lowercase log of a complex number, right? Which we just defined as the capital log, which is the log function that takes real numbers in, plus the principal value of the argument of c, plus, oh, sorry, yeah, I forgot an I here, plus 2n pi I, where n equal to 0, plus or minus 1, plus or minus 2, so on and so forth, right?
Should be the modulus of c for the capital log.
Oh, yeah, sorry. Good, thank you. Okay, so this is multi-valued, right? We can pick n to be anything, and this is one of the many values of lowercase log of c. Okay, so for n large enough, what can we say? large enough, we can find a value W of log of C. Where W is greater than 1 over epsilon for any, modulus. Modulus of W is greater than 1 over epsilon for any positive real epsilon. Right? So given a positive real epsilon, we can pick n large enough so that the modulus of W is greater, arbitrarily large, right? Greater than 1 over any positive epsilon. Okay, so then we just set Z equal to 1 over W, which implies that the modulus of Z is less than epsilon, right? That is to say, here's Z equals 0, I'll say Z not equals 0, and here's some point Z. Here's epsilon, arbitrarily small ball around the origin is where I've arranged my point Z to be. Okay? So then what? If I look at e to the 1 over z, I get e to the w, e to the log of c, which is just c. Right? So, in other words, I constructed this complex number z, that when I put it into my function f, I get out c. And I constructed z so that it was arbitrarily close to the singularity. So that is to say, any non-zero complex number is assumed as a value of this function, 1 over e to the z, in any neighborhood, no matter how small I make it. Yeah?
Does that kind of imply like some relationship between multi-value functions and essential singularities? In the fact that there has to be that, like, you choose a large n.
So, yeah, there is something you can say about, this helps you integrate around essential singularities in some way. Integrate multi-value functions around essential singularities. We're not going to have time to get to that, but it's in chapter 6, section 7, I think, of our textbook. Yeah, really interesting stuff. But anyway, I think we actually went over a bit. Sorry. See you on Tuesday, and I look forward to reading your drafts over the weekend. Or, you know, like I said, it doesn't have to be a full draft. Just send me whatever progress you have.
So is the possibly one exception always just like the one, potentially the one value that the function can't take? Like either the 1 over z can't take 0, so it's the only one you're never gonna be able to get?
Yeah, it's something like that. To be honest, I'm not totally sure how that, what the conditions on that exception are.
Okay.
Oh, I was like,
Yeah, that's a really good question. I don't know. Oh yeah, and I don't know if you saw my email.
I saw it during the break, yeah.
No, I'm not that.
Yeah, so,
I'm not aware.
here, I photocopied this. Not a great copy, but,
It's okay.
Have a nice
yeah.
weekend.
Yeah, you too. This looks like it got cut off, but it's like missing a letter at the end.
Sure.
Thing. Yeah, and like I said, don't be discouraged by the, when you get to terms that you don't know, either look them up or skip over them. It's
Okay.
really the story that's
That's-
the important.
I've got in my reading of quaternions and octonions, I've gotten used to doing that.
Yeah, sometimes you have to, and then just come back later, like possibly months or years later, right?
Yeah.
That's the case maybe.
Thank you.
In Monday, or on Tuesday's class, are we gonna get to the residue theorem?
That's my goal. Yeah, so,
So Tuesday's the last class?
yeah, Tuesday's the last class.
Wow.
Yeah.
I know. It's because that's like the one theorem I've heard so much about, and like we already kind of know how to do it.
Yeah, so
Yeah.
you know how to do it for rational functions, right?
Yeah. It's
That is to say, applying the Cauchy integral formula for a rational function essentially gives you the residue theorem. But yeah, that's my goal, to get to the residue theorem. We might have to skip over talking about functions which are analytic at the point at infinity in the extended complex plane, which is also a really interesting topic, but I feel like people want to see the residue theorem more. So yeah, I hope so.
That's like the theorem like I think everyone hears about before they take complex analysis.
Yeah.
Like yeah, the theorem.
It's pretty important.
And like some of the homework problems we've done,
Touch on it.
yeah,
Yeah.
or like like you could use the residue theorem to do it. It's like the one about one that like I was trying to find like every way not to say use the residue theorem
Oh, okay.
to say it, but it was like the one about